In this lecture, we will start our discussion of diffusion and dispersion. So far, we have been discussing that transport takes place due to two mechanisms. One is due to convection and the other is due to diffusion. Convection is transport due to the fluid flow, due to the fluid velocity. It is directional and it takes place along the direction of the fluid flow velocity, along the streamlines of the flow. Transport across streamlines and across surfaces cannot take place due to convection, because there is no velocity component in that direction. Convection takes place only along the direction of the velocity. Therefore, transport across streamlines and transport across surfaces has to necessarily take place due to diffusion. Diffusion is transport due to the molecular fluctuating velocity. At any temperature above absolute zero, all molecules have a fluctuating velocity. In solids, they fluctuate about a fixed location, whereas in liquids and gases, they randomly move about. They do not fluctuate about a fixed position, but rather they constantly diffuse in space. And this diffusion is what results in transport of mass, momentum and energy. Even when there is no fluid flow, diffusion still takes place, because the molecular fluctuating velocity is non-zero. As you know from equipartition of energy, the energy in each translational mode is equal to half kT. So, half mv square is half kT, which means that the RMS velocity is square root of 3 by 2 kT. That is the fluctuating velocity of the molecules. And it is this that leads to diffusion. The motion of the molecules, the random motion of the molecules is always isotropic. That is, the molecular motion itself has no preferred direction. There is no preference for going to the right or to the left, or going upwards or downwards as far as molecules are concerned. The fluctuating velocity is always has an equal average magnitude in each direction. However, when there is a variation in the concentration, this fluctuating velocity, which is isotropic, leads to a net diffusion of molecules. So, if there is the concentration of molecules of a particular species above a surface is higher than that below the surface, even though the number of molecules going down and up across that surface is the same, there will be a net diffusion, because one particular species molecules will preferentially move downwards. So, therefore, the direction of diffusion is the direction of variation in the concentration, temperature or momentum. So, diffusion takes place along the direction where there is a concentration variation, a temperature variation or a velocity variation. Convection, in contrast, takes place in the direction of the fluid flow. So, that is the distinction between convection and diffusion. Here we will discuss the different mechanisms of diffusion and derive constitutive relations. In all of our derivations of constitutive relations, I will be assuming that there are hard sphere molecules. Hard sphere molecules is that molecules can be treated as hard spheres, which do not interact until the distance between the centers of the molecules becomes equal to the molecular diameter. So, there is no general force field between molecules, but rather the hard sphere molecule assumption is that molecules exert a force on each other only when their surfaces are in contact. So, if for example, I were to express the force as a function of distance, or the force as a function of distance between two molecules. Okay. Okay. And this is the molecular diameter, then the force is 0 until the surfaces come into contact, at which point the force goes to infinity, because the molecules cannot penetrate each other, they are hard spheres. Okay. I should note that this is only a model. Okay. Real molecules do not follow this. Okay. In the case of real molecules, there is a gentle force between pairs of molecules. Okay. Okay. If I plot force versus distance for real molecules, these will experience actually an attractive force up to a certain distance, and when when the distance becomes smaller than a certain value, the force becomes repulsive. Okay. Here negative implies an attractive force towards each other, and a positive force is a repulsive force. Okay. So, real molecules have a force field that looks something like this. When they are very far away, there is no force. At some intermediate distance, there is an attractive force between molecules. When they come still closer to each other, there is a repulsive force. Okay. I will not take into account these complexities during our discussion. I will assume that the molecules are hard sphere molecules. Okay. And for that reason, the diffusion coefficients that I will calculate in this course, the diffusivities are all proportional to the square root of the absolute temperature. Okay. For hard sphere molecules, it will turn out that all diffusivities will be proportional to the square root of the absolute temperature. That is not always strictly true. Okay. If the molecules do not have this hard sphere interaction, but rather they have attractive and repulsive potentials, the diffusivities are not proportional to the square root of the absolute temperature. Okay. They have other dependencies. But to illustrate the physics, I will use the simple model where I consider only hard sphere molecules, and in this case all of these diffusivities will be related to the square root of the temperature. Okay. And based upon these, I will calculate the constitutive relations. Okay. When discussing gases, once again we will assume that ideal gas law applies. That is an approximation, of course, and that approximation is poorer and high densities, okay, when you have dense gases. But for the present, I will assume that the hard sphere approximation applies and the ideal gas law applies for gases. Okay. So, that is as far as diffusion is concerned. Okay. As far as diffusion is concerned. Okay. Now, what is dispersion? I said that convection is transport along with the fluid flow. Okay. And when we discussed laminar and turbulent flows, if you recall, in a laminar flow you have straight smooth streamlines with no cross stream velocity fluctuations, whereas in the case of turbulent flows you have intense cross stream fluctuations and eddies, which are parcels of fluid in correlated motion of a range of length scales. If I were to separate out the velocity into a mean velocity, a time average velocity, which is along the axis of the pipe on average, and a fluctuating velocity, which is the difference between the instantaneous and the mean velocities. Okay. So, if I separate out the velocity into a mean velocity, the average flow velocity and the fluctuating velocity, there is convection due to both the average velocity and the fluctuating velocity, the turbulent fluctuations. Transport due to turbulent fluctuations is what is called dispersion. It is convective transport, but due to the fluctuating velocity of the molecules. Okay. Similarly, when we see flow through a packed column, for example, if we look at examine the system on a length scale larger than the particle equivalent diameter or the packing length scale. If you look at the system on a larger length scale, the flow on average is upward as the fluid passes through the voids between the particles, it does undergo a tortuous path between the voids, but on average the velocity is upward. So, if I were to separate out the velocity into two parts, one is the mean velocity, the mean upward velocity, okay, which is the average over a length scale larger than the particle size, and the difference between the local and the mean velocity, which is a fluctuating velocity, which fluctuates spatially. Okay, it has different directions at different points depending upon the orientation of the voids. Okay. The transport due to that spatial fluctuating velocity is what is called dispersion. Okay. So, that is the distinction between diffusion and dispersion. Diffusion is due to the molecular fluctuating velocity. The dispersion is due to the fluid fluctuating velocity based upon the separation of the flow field into a mean velocity and a fluctuating velocity. Okay. So, we will look at both dispersion and diffusion. First, at diffusion, using, as I said earlier, the hard sphere model for the molecules. This may not be strictly applicable for example, diatomic or polyatomic molecules, because they are not hard spheres. However, we will approximate them as spheres with a particular molecular diameter, okay, and then look at the diffusion process for these molecules, and with the ideal gas assumption, with the caveat that the temperature dependencies for real molecular systems might be more complicated than the simple model that we use here. The model that we use here is derived basically to make estimates of these diffusion coefficients and not for quantitatively accurate predictions. So, let us look first at mass diffusion. Okay. So, let us say I have two chambers consisting of two different types of molecules, A and B. Okay. Let us assume they have equal molecular mass for the present. Okay. And if I have a valve between these two chambers, okay, so I have two different types of molecules. And each of these molecules is in fluctuating motion, random fluctuating motion, okay, in all directions. There is no net motion of the molecules on average. Okay. Let us assume that the system was entirely at the constant density. Okay. If I look at a surface within the system, okay. So, this is the surface, I will call it as Z is equal to Z naught, okay. And I have both blue and red molecules, okay, on either side. But there is a gradient, okay. There is a higher fraction of blue molecules above the surface, and there is a lower fraction of blue molecules below the surface, okay. And all of these molecules are in some random motion, so that on average there is no net motion of the molecules. Okay, so there is no net motion of the molecules. And if I define the concentration as a function of Z of one particular type of molecules, the blue molecules say, there will be a variation in the concentration. Okay. And if I wait with time, okay, even though there is no net transport of molecules, each molecule has equal probability of going upward or downward. If there is a concentration variation in one of the molecules, okay, if there is a variation in the concentration of one of these two molecules, on average you will have a larger number of the blue molecules coming downward and a larger number of the red molecules going upward, and therefore, there will be a concentration diffusion. Okay. Even though there is no net transport of molecules, if the molecular weights are the same, there will be a net transport of molecules, and that is what is called diffusive transport. Okay. And the reason for that is the following. Okay. The molecules on average that are coming downward do not originate at the surface itself. Okay. They originate, okay, at some distance b lambda above the surface, okay, where lambda is what is called the mean free path, or the distance between successive collisions of the molecule. Okay. A molecule coming downward, okay, will collide with a molecule upward and then come down through the surface where it undergoes another collision. So, it originates at a distance approximately b lambda above the surface. Okay. Similarly, a molecule that is going upward originates at a distance that is approximately b lambda below the surface. Okay. And at the location b lambda above the surface, the concentration of A is higher. So, you will have a greater flux coming downwards than going upwards because of this difference in the concentration at locations that are separated by approximately one mean free path. Okay. So, let us estimate what is the flux of molecules due to this upward and the downward motion of the molecules. Okay. The flux coming downward, Jz coming downward, okay, is equal to some coefficient, okay, into Vrms into the concentration of A at a distance z naught plus b lambda. B is a number of order 1, okay, and Aj is also a coefficient of order 1. Okay. Okay. So, I am saying that it comes from a distance of the order of a mean free path above the surface for the molecules going downwards, and a molecule going upwards is going up from a distance of the order of a mean free path below the surface. Okay. So, therefore, the molecule going up Ca at z naught minus b lambda. Okay. That is the flux. Okay. Note that we had earlier when we discussed convection, we said that the convection flux is equal to the velocity perpendicular to the surface times the concentration. Okay. For the molecules above the surface, the velocity component perpendicular to the surface is not exactly the root mean square velocity, because the molecules move isotropically. So, they have equal velocities in all directions. Molecules that are coming down will have some fraction Aj times Vrms is the average velocity of those molecules perpendicular to the surface. Okay. It is not Vrms itself, okay, because Vrms is the random isotropic fluctuating velocity. That is why you have this factor of A, and the factor B is because the molecules coming downward come from a distance of the order of, okay, B times lambda above the surface. Okay. So, the net flux Jz is equal to A Vrms Ca, okay, at z naught minus b lambda, flux upward minus the flux downwards, Aj Vrms Ca at z naught plus b lambda. Okay. Note that lambda is the microscopic scale, the mean free path is the microscopic scale in this case. Okay. And if the mean free path is much smaller than the system size, okay, in this particular case the system size would be, for example, this distance L over which the diffusion takes place. If the mean free path is much smaller than the system size, then I can use a Taylor series expansion for Ca, z naught plus b lambda is equal to Ca at z naught plus B lambda the derivative evaluated at Z naught. Okay, plus etc. And C A at Z naught minus B lambda is equal to C A at Z naught minus B lambda. Okay. So, the first correction will scale as lambda divided by the characteristic length, because the concentration dCA by dZ will be approximately Ca by L. Okay. Okay. It varies over the length scale of the characteristic length. So, the first term will go as lambda by L, the second term as lambda by L the whole square, etc. And when the microscopic length scale lambda is much smaller than the system size, that lambda by L is a small number. So, you can include just the first term in the series. Okay. So, substituting this Taylor series expansion here, I will get AJ VRMS into Ca at Z naught minus B lambda dCA by dZ at Z naught minus Ca at Z naught plus B lambda dCA by dZ. dZ at Z naught, okay, plus higher order terms of course, which we will neglect here. Okay. So, that is the expression for the flux, and you can easily verify that these terms will cancel out, and what I will get in the end is minus 2 AJ VRMS B lambda dCA by dZ. Okay, so, that is the final expression. Compare this with Fick's law for diffusion. Okay, compare this with Fick's law for diffusion. J A is equal to minus D dCA by dZ. Okay. And you can see that this whole term here is a diffusion coefficient. Okay. So, therefore, the diffusion coefficient is equal to AJ B VRMS into lambda. Okay. These first two terms here are just some unknown constant multiplied by the root mean square velocity VRMS and the mean free path lambda. Okay. So, the diffusion coefficient, the mass diffusion coefficient which we get from Fick's law for diffusion, we have estimated the value of the diffusivity by just looking at molecules moving across a surface when there is a concentration variation across the surface. The diffusion coefficient is proportional to the product of the molecular velocity VRMS and the mean free path, which is the molecular length scale in a gas. Okay. So, the diffusion coefficient is proportional to VRMS times lambda. Okay. So, next how do we evaluate these two? Okay. The root mean square velocity and the mean free path. VRMS is determined from the equipartition of energy for the translational modes. There is equipartition of half kT in each mode, in the 3 translational modes, the 2 or 3 rotational modes, the vibrational modes and so on. For the 3 translational modes, half m VRMS square is equal to 3 by 2 kB T, where kB is the Boltzmann constant. and therefore, Vrms is equal to square root of 3 kb T by m, where m is the molecular mass. Okay. So, that is an estimate for the molecular fluctuating velocities. Okay. So, let us examine some typical molecular fluctuating velocities that we would encounter in real applications. Okay. Estimate Vrms for hydrogen, oxygen, nitrogen at 300 K and atmospheric pressure. Okay. So, first let us take the example of hydrogen. Okay. Molecular mass. Okay. The molecular mass is 2 gram per mole, okay, 2 gram per gram mole. 2 gram is 2 into 10 power minus 3 kg. 1 gram mole is 6.023 into 10 power 23 molecules. Okay. And this is 3.32 into 10 power minus 27 kg. Okay. So, Vrms is equal to root of 3 kb T by m is equal to 3 Boltzmann constant 1.38 into minus 20 kg, sorry, joules per. Yeah. Joules per Kelvin into the temperature, which is 300 Kelvin, okay, divided by m, which is 3.32 into 10 power minus 27 kg. This whole thing taken square root of, okay, square root of this whole thing. Okay. And you can estimate, evaluate this is approximately 1934 meters per second. Okay. Therefore, the molecules in hydrogen gas at 300 degrees centigrade are moving at approximately 2000 meters per second. Okay. Oxygen, molecular weight is equal to 32. Okay. And Vrms is equal to square root of 3 kb T by m. Okay. And since the mass of oxygen is 16 times the mass of hydrogen, the velocity in oxygen will be 1/4, 1 over square root of mass. Okay. So, it will be 1/4, which is about 483 meters per second. Okay. And similarly for nitrogen, m is equal to 28. Okay. And the velocity is slightly higher than oxygen, this is about 517. Okay. So, the velocity, the root means molecular fluctuating velocity is about 2000 meters per second in hydrogen gas and about 500 in oxygen and nitrogen gas, and this is comparable to the speed of sound. The speed of sound in hydrogen is about 1290 meters per second, and in air it is about 330 meters per second. So, that is the molecular fluctuating velocity, the magnitude of the molecular fluctuating velocity in gases. Okay. So, there were two things, two factors in apart from dimensionless constants. There were two factors in the diffusion coefficient, molecular fluctuating velocity and the mean free path. Here we have calculated the molecular fluctuating velocity. In the next lecture, we will calculate the mean free path and then go ahead to make estimates of the diffusion coefficient in gases using kinetic theory of gases. I will continue this in the next lecture. This is mass diffusion in gases. Okay. We will calculate the mean free path and then the diffusion coefficient in the next lecture. I will continue this in the next lecture. I will see you then.